So they take the audio and they convert it to this log mel spectrogram. They then send that through 1D conv with some activations. They add some positional encodings, and then they use just encoder block stack. What is going on, guys? Welcome back to another video. In this one, we're taking a look at the very exciting Whisper that was released a while ago, about 2 or 3 months ago. And it's really taken the machine learning community by surprise. First of all, that OpenAI actually released the weights, and made it public. That was good. And also that, the simplicity of this paper is quite remarking in that, the model and everything is very simple, but still it is able to perform so well, and outperform sort of all the previous transcription services, and is much better than YouTube, for example, YouTube transcript, and so on. So let's see. So Whisper is the paper that it's called, but the title is actually Robust Speech Recognition via Large-Scale Weak Supervision. All right, so they trained simply to predict large amounts of transcript of audio on the internet. We scaled to 680,000 hours, so that an insane amount of data. Resulting models generalize well. They're often competitive with prior fully supervised results, but in a zero-shot transfer setting without the need for any fine-tuning. So this is, amazing, isn't that, it performs really well. If you try this out, if you try Whisper, you'll see that you'll become surprised. It really works in a variety of settings. It's really robust to noise. It's robust to sort of background audio. It's robust to different accents, all of that stuff. So I think it works really, really well in practice, and it's also multilingual, so it can also do it for multiple languages. All right, so the introduction here. They mentioned Wave to Vec, which is a previous approach that was able to scale up to 1 million hours of training data. And they say that this is far more than the 1,000 or so hours typical of an academic supervised data set. So you can imagine, the data set that we have available for transcription, where we have human labeled, that's not that many hours. So self-supervised approaches or unsupervised for Wave to Vec is basically an audio to audio sort of architecture where they basically mask some of the input and then ask it to predict, kind of like BERT. So using self-supervised learning, I would say. And that way they can use sort of, just a bunch of audio. And by that, you get a really good encoder that can understand audio. But then you need to do some fine tuning on a supervised data set to get it to be able to produce the captions. So they mention here, these pre-trained autoencoders learn high quality representations of speech, but because they lack an equivalent performance decoder mapping, they necessitating fine-tuning. They say that there is a risk with requiring fine-tuning, because the models become exceedingly adept at finding patterns within a training data set. So this is actually, and they go into more detail here, where sort of there are specific patterns in the training data that when you train it on that specific data set, even if you have your validation and test set, they still have the same patterns in the data, and so it can utilize these patterns to improve on that particular data set, but it doesn't perform well on other data sets. So they say here that in a particularly disturbing example, document 9.2 increase in object classification accuracy when fine-tuning a computer vision model on ImageNet without observing any improvement in average accuracy when classifying the same object on several other natural image datasets. So, this is something that we should be careful with, that it might perform really well on specific data set. They'll talk about that later on in this paper as well. Speech recognition systems that are pre-trained in a supervised fashion across many data sets exhibit higher robustness. So, key here is to use sort of multiple different data sources where we can become robust to these specific patterns in each of the data sets that was collected. They also say that, however, there is still only a moderate amount of this data easily available. SpeechStew mixes together 7 existing data sets, totaling 5,000 hours of supervision. So I've written here basically nothing, right? If you imagine this was trained in 1 million hours, 5,000 hours is, that's nothing in comparison. So the key here is how can we increase this, where this data set is sort of, as they mentioned, gold standard human validated transcripts. But if we can weaken that requirement, then we can build up to get a higher number of training data. So they say we can make use of automated pipelines to scale weakly supervised speech recognition to 10,000 and 30,000 hours of noisier training data. So this paper made use of that. And then they said this trade-off between quality and quantity is often the right call. So even if some data is bad, it's still better to include having that larger data set, even though it's not of the utmost sort of perfect quality, is oftentimes better than not having it. So this is the contribution basically of this paper. In this work, we closed that gap, scaling weakly supervised speech recognition the next order of magnitude to 680,000 hours of labeled audio data. And we call our approach Whisper. Of those 680,000 hours of audio, 117,000 hours cover 96 other languages. And the dataset also includes 125,000 hours of X to English translation data. So I think this is when it's spoken in one language, then basically the caption or the transcription for that is in English, so they can use that for translation. We find that for sufficiently large models, there is no drawback and even benefit, and there are even benefits to joint multilingual and multitask training. So this is interesting. If we have sufficiently large models, it can become better at a particular language by learning other languages. So that's pretty interesting, but makes sense. All right, so here they go. Basically, how did they collect that large of a data set? They developed many heuristics to detect and remove machine-generated transcripts. They say an all uppercase or all lowercase transcription is very unlikely to be human-generated, for example. They also use an audio language detector, which was created by fine-tuning a prototype model. So this is actually very important because how they, basically you just send in an audio clip, and we'll go into the architecture in more detail, but you send in an audio clip, then it's asked to predict what's said in the input. But so if you just send in sort of any language, it's actually still gonna most likely predict English because that's the most common output. But if you predict the language, or if you know the language that's spoken, you can limit specifically you can limit the tokenizer so that it's using that specific language, and sort of in that way we get specific language level output. So yeah, that's maybe a little bit unnecessary detail, but that's how they use they sort of detect the language first, and then they use that in the model later on. But they also use that language detector to ensure that the spoken language matches the language of the transcript. And they say we make an exception if the transcript language is English and add these paired to the data set as translation examples instead. Now, obviously, if you send in a long audio, sort of most data sets is actually just a few seconds in duration. But in practice, if you want to use this in real world, you might want to make subtitles for a movie or something, then it's going to be like 2 hours long. So they break the audio files into 30-second segments paired with the subset of the transcript that occurs within that time segment. And they also train on no speech, and they then use these for voice activity detection. All right, so for the model, how did they actually look at the model? They chose an encoder decoder transformer. So just vanilla transformer. They didn't do anything remarkable in the model. And also they said to avoid confounding our findings with model improvement. So they kind of wanted to keep it simple. But it's sort of a conversion from Hertz to Mel, where the idea is that this is a better representation of how humans understand speech. But yeah, so it's just a conversion, and that's what's used as input to the model later on. All right, so they say here there are many different tasks that can be performed on the same input audio signal. We can do transcription, translation, voice activity detection, alignment, and language identification. So there's a lot. And what they do is that we tell the model exactly what it is that we do by sending in tokens. So they say here, for this kind of one-to-many mapping, to work with a single model, some form of task specification is necessary. We use a simple format to specify all the tasks and conditioning information as a sequence of input tokens to the decoder. So they say, since our decoder is an audio conditional language model, we also train it to condition on the history of text in the transcript in the hope that it will learn to use longer range text context to resolve ambiguous audio. Specifically with some probability, we add the transcript text preceding the current audio segment to the decoder's context. We indicate the beginning of a prediction with start of transcript token. Okay, so all right. So they just use a token, in this case, start of transcript token, to indicate, where do we want to actually start transcribing? Where is the audio and the output matching? So first, they predict the language being spoken, and I already mentioned that for specifying which output they want, and they do that by limiting the tokenizer to that specific language. And in the case where there is no speech, the model is trained to predict a no speech token. The next token specifies the task, either it's transcription or translation, and they do a token transcribe, translate. And then they also predict timestamps, so they predict basically, here is the time or the start of this sentence, here is the end of that sentence, and I'll explain more why that's important in just a second. But so for timestamp prediction, we predict time relative to the current audio segment, quantizing all times to the nearest 20 milliseconds. We interleave the prediction with the caption tokens. The start time token is predicted before each caption's text, and the end time token is predicted after. When a final transcript segment is only partially included in the current 30-second audio chunk, we predict only its start time token for the segment when in timestamp mode to indicate that the subsequent decoding should be performed on an audio window aligned with that time. Otherwise, we truncate the audio to not include that segment. Lastly, we add a end of transcript token. So this is actually, very important, right? Because what this tells us is that basically they send in a 30-second window, but then what if you sort of cut it at the middle of a sentence? Then you want to adjust the window in a specific way. And how you want to adjust the window is dependent upon the start time token, sort of the time for it. And so we predict the token, and if there is no end of transcript, then we know that our next 30-second window should probably start at that point, because we can't include it as it wasn't, sort of the sentence wasn't finished. This is actually, I think, sort of the most thing that's tricky, or I don't know, I want to say annoying, kind of, because this is based on a lot of heuristics. It's based on, it's messy, is what I'm trying to say. how you do this sort of window of movement and so. Basically, the 30-second audio chunk is how they make it feasible, because obviously we can't use all of that in memory, but it also requires some pretty sort of a lot of rule-based stuff to make it work in practice for long format. So here is perhaps the most important part of the paper, which is a figure of how the model works. So they take the audio and they convert it to this log-mel spectrogram, and they then send that through 1D conv with some activations. They add some positional encodings, and then they use just encoder blocks stacked to process the audio. And they use that. They basically send in sort of the information to the decoder, where the decoder is to predict what was said in this specific audio. So here, first of all, they have these different tokens, right? Here's the start of transcript token. Here is the token indicating the language, so English. Here's the task, transcribe, or we can do translate. Here is the time step token. So if we are, if we're not predicting timestamp, then we would add another, no, I think it was like this, no timestamp, something like this. Yeah. So otherwise, then we want to predict the time step, and then they add the time here. So we start at 00. And again, this is relative, I think, to the audio clip that we send in. So, which is 30 seconds. So it's going to be, I guess it's like, this is 0.0 seconds, and then it's rounded to 20 milliseconds. And then we'll have one later on for the end here, which will also be green, right, for the end time. All right, so then we have the text, and so they start at, this is just the input, and then we want to predict and then this is input as the next, right? This is basically how transformers work, and I'm sort of assuming you know how transformers work for this. Otherwise, this might look really confusing. But yeah, I think Yannick has a paper walkthrough on attention is all you need. And I've also implemented it from scratch if you're interested in knowing the details of how it works. But yeah, so that's basically the architecture. It's super simple. And they have these tokens to specify the task, start of transcript, and so on. And then they have this multitask training format where sometimes we're conditioning on previous text. And then we have this start of transcript. So we have some previous text. We had to have this start of transcript. And then we specify the language tag if there is speech. And then otherwise no speech. And then we look, what is the task? Do we want to transcribe or translate? And then depending, do we want no timestamps? Depending on the next token, then we predict just the text. And then we predict end of sentence. Yeah, so, or if we want to transcribe, then we send in the begin text. This is 00. We do the text tokens, and then we specify the end time of this sentence. Then we have another begin time and so on. And this is used most importantly for the shifting of the 30-second window, where, if it's the case that we have begin time and then we have some text and then we don't have an end time because there's still talking going on, then we know that we need to adjust the 30-second window and sort of it should start with this because it wasn't finished. That might have been a little bit quick, but hopefully you get the gist of how the architecture looks like here and how it works. And let's continue. They have different models here. They have tiny, base, small, medium, and large. And this is also interesting that they have released a bit silently these, I think it was just a few days ago, a large V2 that was had some, I think it was a few percentage improvement from the previous one. And, interestingly, the large one is not that large. It just has 1.5 billion parameters. which most people can run, or many people can run on their GPU. If you look at the relative speed, it's sort of 1x for large, the relative speed difference. We have 1x for large, 2 for medium, 6 times for small, 16 for base, and 32 for tiny. And the tiny one is really tiny. It's just 40 million parameters. So let's see. So here they mention speech recognition research typically evaluates and compares system based on the word error rate, WER metric. And the WER is based on a string edit distance. And they talk about here that it causes problems because of sort of specific styles that different data sets can have, which impacts the error rate for this. So it's not the perfect metric, as it's data set specific, depending on how they labeled it. So basically all they talk about here is that they had to do a bunch of manual stuff to make it better, because they manually adapted it to this specific data set to get a better score. But if you look at the figures, which might be most important here for the results, here are the blue one here is supervised Libri speech models. And then we have the WER score on another data set, the Libri speech. So this is trained on Common Voice, Chime, and TED Lium, some data sets. And it improves quite markedly, like it improves a lot when you train it on that. But as you can see, it's not a linear correlation between the score on another data set. So what this tells us is that it improves on the particular data set that you trained on, but it doesn't generalize to another data set. But if you look at the Whisper model, you can see that it has a much better correlation on the improvement on one data set to the improvement of another data set. And specifically, you can see here also in this table, you can see that I believe this is zero-shot performance. So zero-shot performance is the same on the dataset that it has specifically been trained on, this VAVE to VEC, that it's been supervised on. So there's no difference in the error rate. But if we look at the comparison between all of these other datasets, we can see that the difference favors Whisper immensely. So they really want to mention or get across that dataset specific improvements does not always generalize well. So we should be careful, and maybe we should even evaluate on data sets that we haven't trained on to actually know the generalization performance, because this standard train test validation split doesn't even that doesn't generalize, because the data set can be have these specific patterns that humans can't pick up, but these models can. All right, so let's see. Basically, that's what it says here. Okay, so this is average relative error reduction. This is the RER here. Whisper model achieves an average of 55% reduction when evaluated on other speech recognition datasets. This finding suggests emphasizing zero-shot and out-of-distribution evaluations of models, particularly when attempting to compare to human performance, to avoid overstating the capabilities of machine learning systems due to misleading comparisons. Here we have a figure showing that basically the more data you have, this is not a linear scale, but the correlation is linear. This is logarithmic, and so we can see that basically, if you have more data, it improves the error rate. So there's quite clear correlation there. But for the translation, it's not clear. The correlation for transcription is 0.84, so very high. But the correlation for translation is only 0.24. And then they have some theory as to why that is. Here they say that a clear trend of improvement is in training data, but not for translation. We suspect this is partly caused by the noisier training data due to errors in audio language identification. Inspection shows that the majority of supposedly Welsh translation data is actually English audio with English captions, where the English audio was misclassified. So basically, they believe that this could be that their audio language detection model is bad, so they don't actually get correct data sets here. But it might also be, a more difficult task, maybe. I don't know. So then they have this also, where they have signal to noise. So what this tells us, these two figures right here, is that Whisper is really robust to noise, where if we increase the noise, they mentioned signal to noise, white noise, and then pub noise, we can see that the others models sort of become much worse faster than Whisper. So yeah, the other models degrade faster. So it's robust in that way, which is interesting. And here they say that the language identification part is not competitive with prior supervised work and underperforms by quite a lot. So this is perhaps one of the things to work on. So sort of a future iteration for Whisper is to improve the language identification part. They also say here that long-form transcription is very difficult because of this 30-second audio chunk. And they say this is not a problem with most academic data sets, but presents challenge in real-world applications, which often requires transcribing minutes or hours-long audio. We developed a strategy to perform buffered transcription of long audio by consecutively transcribing 30-second segments and shifting the video according to timestamps predicted by the model. We observed that it is crucial to have beam surf and temperature scheduling based on the repetitiveness and the long probability of the model predictions in order to reliably transcribe long audio. So basically, it's messy, and there's a lot of heuristics and stuff to make this work based on these 30-second audio chunks. And I think this is general, if we look at GPT and all of these models as well, basically all transformer models where we have very long format input, like let's say we are trying to summarize a book using GPT, then it becomes very difficult to have this sort of long form dependencies, right? Because earlier parts might be indicative of what sort of the next chapter prediction should be, etc. But this is sort of a general issue, I would say, with the architecture of transformers. And it's not clear how you would solve it in this case. All right, so basically here another result is that Whisper is competitive with state-of-the-art commercial. It performs really well on data sets that have long-form transcription using this heuristic-based stuff that they've done. So Whisper is competitive with all other, better than all other automatic transcription services. It's sort of on the same level as humans, but if we look at the best part is when humans interact and use in collaboration with some machine generated. And let's see if there was anything else I wanted to touch on. Yeah, here we can see basically the improvement as we scale the model. So larger model is better, but we see some bottleneck here. When we double it, it doesn't increase very much or improve very much. Similarly here, multilingual, so basically it starts to flatten pretty quickly after the medium to large one, and there's a 2x difference in relative speed between them. And then if you look at the data set size, they use a subset of the data set. We can see that it improves a lot up to about 13,000, and then it slowly lowers the improvement from 13 to 50,000 hours, and then increasing from 50,000 hours to 680,000. There's a very low, just a one single point improvement. So perhaps having about 50,000 hours is the sort of, if you have that, then you're good, I guess. It doesn't improve that much, but it would be interesting to know, how much of these 680,000 are bad audio as well, and how much lower could you get this if you would remove all the audio that's wrong, because most likely there's a lot of stuff in that aren't very good, because there's just no way of going through that much data. Here we can see that for low models, because the models have a .en extension so that you can use only English version. So for example, you can use, let's see, you can use large.en, or you can just use large, or tiny and tiny.en. And we can see that for the small models, this actually matters. So for the small models, there's only having only English and not training on multilingual tasks make it better. But for large models, then it's actually better to have multilingual data on the performance on English specifically. So sorry, this doesn't exist, the large.en, because as we can see, the large.en is actually worse at English than the large one. So there's no point in having large.en. But for the medium one, it's sort of very, I don't know where medium is, but it's very, it doesn't matter much. So basically, if you're going to use it, I wouldn't use .en extension, except if you're using like the tiny one. All right, and I think I'm gonna skip this. This is the strategy for reliable long form transcription. All I want to say here is that it's like really hacky. They're using beam search with log probability, and then they use this increasing temperature that scales, and they have these different rules for when to apply and predict no speech and so on. It's messy. So anyways, basically like the most key point that we want to improve, if we would want to, Whisper is really good, obviously, but if there's something that we would want to improve, then it's the reliability of long form decoding, so that we find a better way of doing this, because I mean this is no bueno. Like this is yeah, I don't want to. This is really hacky stuff. And then they mention here that just the improvement of these stuff they've added with this temperature fallback and all this stuff, that's not that important, I would say, for understanding the core of the paper. All right, so that's it for the Whisper paper. Hopefully the video wasn't too long and you could follow it. Let me know if you would like future videos on Whisper. I've played around with fine-tuning the model, and I'm building sort of a project with Whisper that I might make videos on. So let me know if you also want to see how you can fine-tune this model. All right, so with that said, I hope you enjoyed this video. Hope it was useful in learning about Whisper. Let me know your thoughts, and thank you so much for watching the video, and I hope to see you in the next one.